物理学家尼尔斯·波尔和维尔纳·海森堡于1927年在丹麦哥本哈根合作研究时，共同提出了哥本哈根诠释。该理论提出通过波动方程来描述量子力学中的量子态，用以解释科学家们在20世纪早期发现的很多经典物理完全无法解释的新颖的量子现象，比如波粒二象性以及观察者效应。1935年，在与爱因斯坦就 EPR 论文及量子纠缠现象的信件讨论中，薛定谔提出了一个关于猫的思维实验，用以揭示当时量子学界理论的不完整性。薛定谔提出了一个尖锐的问题：当时的科学界如果接受哥本哈根诠释，即量子世界中的一切物质以波方程的不确定性的形式存在，那么一只处在宏观世界的猫，一直到实验员打开猫屋的那一刻，可以处在既是活着又是死了的叠加态。这个著名的思想实验至今仍然是量子学界理论的试金石。如何完整的诠释量子世界的奇特现象，同时又不与宏观世界里的经典物理学相违背，科学界至今还没有找到答案。猫真的可以既是死的又是活着的吗？在本期视频中，托马斯坎贝尔将为您从概率统计分布和虚拟现实的角度，为薛定谔的猫实验做出崭新的诠释。
All right, so here is going to be a Schrodinger's cat thought experiment. Now, what you see in front of you is a hemisphere, a dome. That's going to be our cat house. And this cat house is actually a house that houses a cat, so don't get too excited about a cat house. We're going to put a cat in there. And, well, actually, I'm not going to put a picture of a cat in there because the whole point is to kill the cat, and that's not very sensitive. So this is going to be an invisible cat. You're just going to have to imagine that the cat's in there because invisible cats, they won't be hurt. So there's a cat that sits in there, right, curled up around that little red spot in the middle. Now, this little red spot here in the middle, that's right here. This red spot is a radioactive source. And a radioactive source is radioactive because it throws particles off. Particles just shoot off of it, one after the other, but they shoot off at all different directions. So a particle may zing up this way, and then it may zing out that way, and then it might zing out this way. It's random, equally probable to go off in any direction. Now, here, this other little red spot, that's the Geiger counter. That's a sensor. A Geiger counter is a thing that when one of these little particles that's been thrown off hits the Geiger counter, it creates a little electrical pulse, makes the Geiger counter buzz or makes a counter count. It can trip a switch. And in Schrodinger's very devious and dark mind, it released poison. So it hits the Geiger counter. The Geiger counter sends an electrical pulse that dumps a bunch of poison into this poor cat's house, and the cat dies. But it only dies if one of these particles from this radioactive source flies up here and hits that particular spot. Okay? If the particle flies up and goes over here, well, nothing happens. No electrical signal is created in the Geiger counter. No poison is dumped into the cat house. All right. So here are the probabilities. Okay, if the probability of a dead cat, it's basically the area of this Geiger counter divided by the area of this hemisphere, right? That's the probability that a particle coming out randomly is going to hit somewhere. Okay, we're only going to look at particles that come up into this half of the sphere, this hemisphere. The other particles that fly down out of the hemisphere, well, we'll just ignore them. We're only going to look at the particles that fly up. That's why I have over here a little r over 2. That's the number of particles entering the upper hemisphere, because r is the number of particles per unit time leaving the radioactive source. Half of them are going to go in the bottom hemisphere. The other half are going to go in the upper hemisphere. So anyway, so if we take the area of the hemisphere and divide that into the area of this, then that's the probability that some random shot that could hit anywhere inside this hemisphere is actually going to hit here rather than any place else. It's this area divided by all the rest of the area. All right, and that's what we have over here. It's the area of the Geiger counter over the area of the hemisphere. And here I just expanded that a little bit. I've taken the area of a sphere, divided it by 2 with the 1/2, subtracted this little area of the Geiger counter off of it. So that's all the area of the hemisphere except for that little bit of area. And then that defines this AG over AH, A, the Geiger counter area of the hemisphere. All right, and here it is expanded, like I say. Now, down here I have R's, the rate, the number of particles per second that are going to leave this radioactive source. That's how radioactive it is. T, that's the experiment in seconds. It's going to start at T equals 0. At T equals 0, we throw in the cat, throw in this particle, this radioactive source, and that's when it starts, T equals 0. So let's look down at the bottom here. We said that the probability that the cat's going to die from the very first particle is the area of the Geiger counter over area of the hemisphere. Now, we also know that if the cat's alive, in other words, if that first particle hit someplace else on the hemisphere and didn't hit the Geiger counter, that's going to be 1 minus the probability that it hit that Geiger counter. See, P dead is the probability it's going to hit the Geiger counter. That's what this is, P dead. Probability is going to hit that Geiger counter. Now, 1 minus that probability is after one particle goes out, the cat's still alive. It's going to be 1 minus P dead, right? Because the cat's either dead or alive. All right. Now, I'm going to fire my second particle out. If my second particle also misses the Geiger counter and hits someplace else in the hemisphere, then it's going to be 1 minus P dead times 1 minus P dead. Those two probabilities multiply because it missed the cat on the first particle and it missed the cat on the second particle. And so you just multiply them. And after n particles have come out, then it's 1 minus P dead to the nth power. You see? So if it's 100 particles have come out, then 1 minus P dead to the 100th power is the probability that the cat is still alive. All right, so that's how all this works out. Again, here the R is divided by 2 because the rate at which particles leave the radioactive source, only half of them are going to leave it and go up to this upper hemisphere. All right, now that I've kind of set up the cat experiment, let's go see how it works out. Okay, now here's a spreadsheet. And if you look at this spreadsheet, here's going to be where we take our measurement here. Measurement T seconds after experiment starts. So it starts at T equals 0, and this is a column for seconds, and it's all seconds until we get over 60 down here. And then so when we get over, here's 57 seconds, and the next one is 1 minute and 2 seconds, you see. So I just keep track of the hours, minutes, and seconds so that it's easier for you to see in these bigger numbers, because otherwise somebody tells you, 10,000 seconds, you won't have any idea what that is, because it's hard to divide everything by 3,600 in your mind. Okay, so here's the measurement that we're going to make. And in 1 second, okay, in 1 second, because I started with R equals 2, I can go up just a little bit and I'll show you here. R for particles is R equals 2. You see that? So that means 2 particles per second come from the radioactive source, and 1 particle per second comes up into the upper hemisphere. Okay. Now, 1 second, 1 particle. That's on the average. So 1 particle is hit, and we see the probability that the cat's still alive, which means the probability that that particle hits someplace else in that hemisphere is 0.99928. And the probability that the cat is dead is 0.0000072. Okay? Now, here, I've converted this ratio. That's a probability alive and dead, and probabilities are just ratios. So I've converted it to probability expressed in integers that are greater than 100. It's exactly the same ratio. So if I do that, then the ratio of 0.999928 to 0.000072 is exactly the same as the ratio of 1,395,784 to 100. You'll just have to trust me on that, or get out your little trusty calculator and see how that works. But these two are in the same ratio as these two. So it's the same probability. It's just really hard to put 0.999 balls in a box, or to put 0.00072 balls in a box. And I like this little picture of the raffle box with balls in it because it makes it easier for you to understand, makes it less abstract. So I've just changed this probability into larger numbers with the same ratio. So no sleight of hand here. I'm just making them so that we can look at it as balls in the box. So in this case, after 1 second, it's like you had this box over here and it had 1,395,784 blue balls in it and 100 red balls in it. And the random draw from the probability distribution of the possibilities is a random draw between this 1,395,784 blue balls and these 100 red balls. If you pull out a red ball, cat's dead. If you pull out a blue ball, cat's alive. And that's the probability if you make the measurement at 1 second. Okay, now remember, making the measurement is what collapses the wave function to a result. Making the measurement means you jerk open the door to the cat box and you look in and see whether the cat's dead or alive. That's making the measurement. So we do that in 1 second, and you see the probability that the cat's alive is very, very high. But that probability is going to go down with time, because the more little bullets you spit out of that source, the higher the probability that one of them is going to hit that Geiger counter and the cat will die. All right. So it's like I've done this experiment all these times. Every row here is like a repetition of the experiment, but at a different time. So here's where I did the experiment, and I opened the door to see if the cat was dead or alive in 1 second. Here, 120 seconds. Here, 240 seconds. Here, 1,080 seconds. Here, 4,020 seconds. Okay, so that's, that 4,020 seconds, wherever it was here, that's, 1 hour, 7 minutes. So in an hour and 7 minutes, I open up that door, and these are the probabilities now of finding the cat alive or dead, which translates into 300 blue balls and just 100 red balls. So if in 1 hour and 7 minutes, I jerk open the door and look, 300 balls are blue, 100 balls are red. I take that random draw, and that cat is likely to be alive, but might be dead. I mean, look up here at 42 seconds, just 42 seconds. It was 505 balls for blue and only 100. So there's 5 times more blue balls than red balls, but look what happened. I got a dead cat. That's because randomness is random. You don't always get something under the fat part of the curve. So I can change the random numbers. What this column is the actual result of the random draw. What I do here is I have some mathematics, some random number generators in mathematics that do the random draw. It looks at, like here in this case, in this dead one, it looks at 505. If there's 505 blue balls and 100 red balls, and you take a random draw, what do you get? Well, in this time, I just happened to grab a red ball. So if I looked then, the cat would have been dead. Even though it's 5 to 1 that would have happened, well, that's what happens, you see. Now, I can push F9 here on my computer, and it recomputes all of those tests. In other words, it's like I did the experiment again. It's like, all right, let's get another 1,000 cats and another 1,000 boxes, and let's do it again. Well, you'll see here, let me lean up and do that. Here, hit F9. That's right here. Now notice when I did that, we've got a dead up here when it's 1,243 to 100. Whoa, but came out dead. Sorry, cat. That's the way it is with random draws. Even if there's only one red ball in there and all the rest are blue balls, you could pull out that one red one, but most of the time you won't. So that's what's going on. So let me just let you look at these. Mostly you're going to get alives up here. Occasionally we just happen to grab a red ball, but as we get down, look at this. Mostly we get dead, and we get down further and the cat's always dead, because now the probability is there only 100 blue balls to, here at the bottom, 48,000 red balls. So it's very likely the cat's going to be dead by 24 hours. And we go up here in the middle someplace. Here's a point that I made up. If exactly 9,675.186 seconds, the probability is 50-50 as I compute it. Depends on how accurate my computations are, but you see it's 0.5, which means there's 100 blue balls and 100.0000123 red balls. Now, if we wanted to actually make that 100.00 whatever, we'd have to multiply each one of those by a much bigger number. So in any case, you see, so there's 100 of each. 100 red ones, 100 blue ones. It's a 50-50 chance. And that happens at 2 hours, 41 minutes, 15.186 seconds. So that's how long it takes before this cat has a 50-50 chance of being still alive. You see? Now, so take a look at these. I'm just going to punch this F9 button, and you'll see every time I'm going to do another random draw for all of these times. So all of these measurements would all be just single measurements, but I've got them all listed down here. Like I did the experiment once at 1 second, I did it again at 2 seconds, I did it again at 4 seconds, and I did it again. And here's all the results. I did all these experiments at all these different times. Okay. Now, if I press this F9, you can watch over here and see how what's dead and what's alive changes. Well, we'll maybe look at this part. Mostly alive, but a few dead in there, and maybe down here where there's more dead, right around the 50-50 chance. So that would be right here. There's one. See how the dead and the lives? There's another one, another one, another one. Oh, that one really got dead just before at the middle there. Another one, another one, another one. See how that works? These are all random draws. So it's not guaranteed at any particular time that the cat would be either dead or alive. Even the very first second, if that very first particle out of that source hit that Geiger counter, the cat would have died on the first second. It's just not likely. So this is how let me go back to that. This is how the Schrodinger's cat actually works. Okay, you can read here. Well, let's look at this. I didn't show you this, but look at these probability lines. Here's the blue probability line. Probability right at time equals 0 is 1. Cat's alive. Haven't started the experiment yet. Cat is resting nicely. As time goes on here, these are seconds, then probability of the cat's alive goes down, 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 and eventually goes to 0 or very, very small. Okay. never actually gets to zero, just gets to like 10 to the minus, something. So very, very small. Now, here's the probability that the cat's dead. It's very unlikely the cat will be dead immediately. And it's zero that the cat's dead at t equals 0. But then as time goes on, the probability of the cat dying goes up and up and up and up. So the way Schrodinger's cat works is you put the cat in the box, and then at any time you make the measurement, a random draw is made from a probability distribution of the possibilities, and that is what the virtual reality renders at that time. So if you happen at this point, let's say where we are right here, here's the first dead that occurs, at 20 minutes. If at 20 minutes in, even though it's much more likely 1,000, 1,104 to 100 that the cat will be alive, well, that time, that random draw pulled out a dead. And when you make that measurement at that time, you get a dead cat. Well, you got one this time when you made that measurement. Every time you do this, it's like a new random draw. You have another cat, it's a different random draw. The next cat's a different random draw. So every line here that we move across, every row, it's a new cat being looked at a different time. You see? Okay, that is Schrodinger's cat within a hemispherical domed cat house. That's how it works. These are the probabilities. It's just, the math is simple. That's why I did this, because it's simple that most everybody can follow this. It's just a very little bit of algebra here. And you see that there is no cat that's both dead and alive. There is no potential cat. There's no superposition of cats. There is just simply a random draw from the probability distribution of the possibilities, and that's the answer. Now, I'm going to also show you how this works in a double slit afterwards, but we're going to do this, and then we're going to do a Zeno paradox, and then we'll do the double slit, and that'll get just a little more complicated because the probability distribution just isn't a binary, dead or alive. Now, the probability distribution is something quite different. It's a interference pattern, and we can say why it's an interference pattern. Why should these single particles position themselves on the screen in an interference pattern? Why would the system do that? I mean, it could be a pattern on a happy face. It could be a little happy face pattern, and that would be more cheerful. But for some reason, the rendering engine decided that it would make those particles line up in an interference pattern. And there's a reason for that. The requirements, the constraints placed on the rendering engine made that necessary. It has to be.
Hello, Tom. Thanks for being here today. I understand you have an update on your Schrodinger's cat experiment.
I do have an update, and I have this update because Tim Martens, a friend of mine, lives in Germany. Matter of fact, he was the guy who kind of was the leader of the translation group that translated My Big Toe from English into German. But anyway, he listened to that talk that you and I did on Schrodinger's cat that's up in the Science Trilogy, and he had a question about it. That's something that didn't quite make sense to him, and he explained it to me. It didn't make sense to me either. So I have a little update for that. He was quite right. It's a detail that I suspect 99% of the people did not notice. Well, I was one of those. I did not notice it, and he caught it, and he is absolutely right. Here's the issue, and that is that I talked about you had these cats, right, in boxes, and you had a radioactive element in there, and there was a Geiger counter, a thing that creates electrical signal when it's hit by a particle from the radioactive output. Radioactive substances throw out particles, And when one of those particles hits this thing, then it creates an electric signal, and that electric signal could do all kinds of things. Now with Schrodinger, that electric signal emptied poison into the cat and killed the cat. But it could just as easily have, say, punctured, that electrical signal could puncture a big balloon full of red paint, and it could spread red paint all over the inside of the cat box. And now no animals would be hurt in this experiment, and everybody could talk about Schrodinger's cat without feeling sorry for the cats, and it would work the same way. Now, what I said was that when the experimenter makes the measurement, in other words, opens the door to see the state of the cat inside, that then the system does the calculation, decides whether the cat should be dead or alive, and that's what you get. Okay, now that is accurate if we were talking about the balloon full of red paint rather than a cat. Okay, that would be how it would work. But because we have a cat in there, Tim told me, we have a consciousness in there, and that consciousness has to be getting a data stream. And let's say just every 100th of a second, the cat gets a data stream update about his environment, because the cat's not perfectly still. The cat's looking around at different things and, licking its paws and doing whatever cats do. So it has a data stream coming to it all the time, every 100th of a second, say, just make up a delta T. That's feeding data to that cat, and it's getting data, it's getting data, it's getting data until that particle hits that sensor and bang, it gets the poison, and then the cat dies. Okay, now after the cat dies, there's no more data stream to send to that cat because the cat's dead now. Okay, so what this means is that I should have said that when the experimenter opens the door, okay, he will find a dead cat or an alive cat. But the cat doesn't have to die the instant the door's opened, or not die. You see, there is no cat is part of the situation. There is no cat. The cat isn't rendered unless somebody's looking at it. But if the cat is conscious, then the cat is looking at the cat. It's licking its paw. It's looking at the inside of the box. So what happens is that the cat dies whenever that 100th of a second delta T happens to find a particle that hits that Geiger counter that sends out the signal that kills the cat, right up until that time. But it may have been 5 minutes later when the experimenter opens the door. Well, now they'll find a cat that's been dead for 5 minutes, you see. So the cat doesn't die when a door is pulled open. The cat dies whenever the cat dies, whenever the particle hits the thing. Now, from that time on, after the cat's dead, then it's just like the paint. It doesn't matter, you see. Now, as long as that cat is in the box, the cat is not in anybody's data stream except the cat's data stream. The cat is in the cat's own data stream. But the experimenter, who can't see the cat, does not get anything in their data stream. So once the cat dies, then there's no cat data stream at all to the cat or to the people or to any place. So then the cat just doesn't exist. But the cat does exist right up to the point when it dies. And then when the experimenter opens the door, he sees a dead cat with a warm body, if it just died recently, or a dead cat with a cold body because it died some time ago, because it's been a long time since the experimenter opened that door, you see. So I just didn't say it quite right. And Tim pointed that out to me, and he is absolutely correct. We do have to realize that that cat had his own little reality going on there right up until the point that he didn't. So what I was saying was accurate for the paint, but not accurate for the cat, because the cat could die before the person opens the door, not just as that measurement's made, because the cat has consciousness too. So that's the little update
that is really fascinating and very impressive, Tim. This will be added to the bonus content on the MBT Science Trilogy.
Yeah.
Really
Good.
interesting. Thank you.
Mhm.